So hello everyone, my name is Nicole Cork. I'm the Association Manager of iHEA's activities. Welcome and thank you for registering for today's webinar, an introduction to construction of discrete choice experiments hosted by our Health Preference Research Special Interest Group. The webinar will run for approximately 60 minutes and will be recorded and uploaded on our website afterwards. Before we begin, I just wanted to run through a couple of housekeeping items. If you do experience any technical issues during the webinar, please write them in the chat box at the bottom of your screen and I'll be happy to assist. Everyone on the line has been muted except for the speakers in an effort to eliminate background noise. So if you do have any questions during the webinar, please use the chat box and they will be addressed at the end. I'm now going to pass it over to Jason Ong, who is one of the conveners of our Health Preference Research Special Interest Group, and he will introduce today's speaker.
Welcome everyone. Thank you so much for your time to join us for today's webinar. So as Nicole said, my name is Jason Ong. I'm a sexual health physician and health economist based in Melbourne in Australia. And I'm one of the conveners of the Health Preference Research Special Interest Group, together with Fern Terrace-Presswold, who's on here, as well as Alec Miners, Matt Quaife, all from the London School of Hygiene and Tropical Medicine in the UK. Please do check out our group if you'd like to learn more about health preference research. So as many of you on the call know, health preference research is dedicated to understanding the value of health and health-related goods and services. And that the mantra in health preference research is choice defines value. And with a better understanding of what patients want, providers, regulators, and policymakers can better meet the patient's needs. And for this, researchers commonly design and conduct studies such as discrete choice experiments, which you'll hear more about today, a survey method that quantitatively measures what people want. We are very fortunate to have Professor Debbie Street share her many pearls of wisdom with us about the construction of DCEs. Professor Street is the head of Choice Modeling Research Group at the Center for Health Economics Research and Evaluation at the University of Technology in Sydney. And her research is in the theoretical construction of optimal designs, and she has focused on discrete choice experiments for the last 20 years or so, and is regarded as one of the gurus in experimental designs of DCEs. So the talk will go for about 45 minutes or so, and we'll use the remaining time for Q&A. And as Nicole mentioned, please add any questions that you have in the chat box, and I'll summarize these for Debbie at the very end. So with this, I'll pass the time to Debbie. Thank you.
Right. Thank you very much, Jason, and thanks for the invitation. Thank you all for coming along, which at what for me is 10 o'clock at night, so forgive any tired and silly comments I might make. So I want to talk about an introduction to constructing discrete choice experiments. But I'd start by looking at a simple discrete choice experiment, look at the design requirements. I'm focusing on the MNL model because it's an introduction and how we go about comparing competing designs. I'm going to talk about the construction of generated developed designs for main effects, briefly discuss how we might extend that to interactions, and conclude by looking at some empirical comparisons of generated developed designs and other designs. So I think of a DCE as having 5 basic features: some screening questions, some background information about the task, the choice context, the choice sets themselves, and possibly some follow-up questions about the task. So I'm going to use an example we did with light bulbs about 10 years ago. And we looked at screening questions, demographic ones, age, gender, and state of residence, to try to be sure we had a representative sample of the Australian community. And then we had a simple screening question: have you ever bought a light bulb? We didn't want people that had no experience of that marketplace. We provided them with background information. At that stage, Australia was about to ban the sale of incandescent light bulbs. And that meant that the light bulbs would be these energy efficient light bulbs. We were interested in how people might go about making decisions. And I've highlighted in the background information, although we didn't for the people, some of the features of the light bulbs that became the attributes. So we gave them a typical survey page, explained the context in which we were asking them to make the choice. Suppose you need to replace a light bulb in your living room, and the room is currently used for talking, reading books, watching TV. You have to replace the bulb with an energy efficient bulb. Which of the light bulbs shown below would you choose? And we actually, for the quality of light, we actually had shown them little indicators on a spectrum about what those qualities looked like. So you can see we've got the part in italics is the choice context. So it's about being in the living room. The choice question, which of the 3 light bulbs would you choose? And the choice set, which if you've done a standard course in design theory, you might think of as a block and a block factorial experiment. And if you haven't, it's just a choice set. So the goal of the choice experiment is to think about how the attribute levels affect the utility of the individual. We're going to assume that individuals make utility maximizing decisions, and that utility has got 2 components: a systematic component relating to the attributes and levels of the items under consideration, and a random component, which might be unobserved determinants of utility, individual characteristics, or random variation that people make when they make choices. So my choice experiment, our choice experiments tonight are going to have capital N choice sets. They're all going to, each choice set will have M options, and they're going to be unlabeled options. So we're thinking about them as just a generic choice problem. We're going to ask respondents which option they would choose from each choice set, so just their favored option. We're going to describe each option by K attributes, and attribute Q will have LQ levels. And I'm going to represent the levels by 0, 1, up to LQ minus 1 for each of the K attributes. So attribute 1 has L1 levels represented by 0 up to L1 minus 1, and so on up to attribute K, with LK levels from 0 to LK minus 1. And a typical option will be a K tuple. So in the K tuple I've got there, it's level 2 of attribute 1, level 1 of attribute 2, level L3 minus 2 of attribute 3, and so on up to LK minus 1 of attribute K. So what properties do we want our DCE to have? Well, we want to have a manageable number of choice sets for the respondents. If you ask them too many, they're going to get confused, they're going to get tired, they may just stop your experiment. We want the choice sets to be statistically efficient. We'll come back to that in a couple of minutes. We want to be able to identify the parameters, ideally have them independently estimated. We don't want repeated choice sets, although we might compromise by having 1 or 2 of those to check consistency for the respondents. We need all the options in a choice set to be distinct, otherwise the respondents can't make a choice sensibly. And we don't want to have an option that's the best in a choice set or the worst in a choice set. Although again, we might have 1 or 2 such choice sets to check that the respondents are behaving in a rational fashion. So here is an example of 4 choice sets that satisfy all of these properties, provided there is at least 1 attribute that doesn't have ordered levels. So here I've got 3 attributes. All 3 attributes are binary, and the options for triples with all entries equal to either 0 or 1, because LQ minus 1 is 2 minus 1, which is 1. And an example of an attribute that doesn't have ordered levels is something like something like color, for instance, because people don't necessarily have a standard order for the color that their color preference. Here's an example for plane tickets, which are a bit topical in the current shutdown situation, where the attributes levels might be cost and check-in time. And if we have 2 costs of $199 and $299, and a check-in time which you must check in 30 minutes before the flight or you forfeit your ticket, or you can check in up to 15 minutes before departure, then a $199 fare with relaxed check-in conditions is going to be preferred by all respondents, all else being equal. And so such an option is said to dominate. And that's what we want to avoid in our choice sets in general. So the design question for choice experiments is quite simple. Given we want to estimate the impact of the attributes on the utility, which level combination should be placed in the same choice set and which choice set should be placed in the same design? So the form of the utility function for main effects of the MNL model, we've got the utility U, and it's got two components, V for the systematic component and E for the unobserved error term. These are specific to the particular individual, the particular alternative within the choice set, and the particular choice set within the design. We're going to assume that the EI, J, C are independent extreme value type 1. And then the probability that item TA is the preferred item from amongst the items T1 to Tm is e to the lambda VA over the sum over J of e to the lambda Vj. And lambda is a positive scale parameter inversely proportional to the variance of the random component and is commonly assumed to be equal to 1. So we want to be able to calculate the VIJC as a function of the attribute levels. So if we think about our main effects model, we're going to replace a level of the attribute Q by a vector of length LQ minus 1. And this is called a coding. And we'll just, for the moment, look at two different codings that are in common use, dummy coding and effects coding. With dummy coding, for each attribute, one level is chosen as the reference level. Each of the other levels are replaced by a row of the identity matrix of order LQ minus 1, and the reference level is replaced by a row of zeros. With effects coding, again, one level is chosen as a reference level, and each of the other levels are replaced by a row of the identity matrix of order LQ minus 1, but now the reference level is replaced by a row of minus 1s. So I'm going to use the EQ5D3L attributes and levels to illustrate this. So with the EQ5D, we have 5 dimensions that describe people's health states: mobility, self-care, usual activities, pain and discomfort, and anxiety and depression. And each of those dimensions has 3 levels: no problems, which I'll think of as level 1, moderate problems, level 2, and extreme problems or unable to, which is level 3. So let's dummy code an option for the main effects MNL model. I'm going to use 1, which is no problems, as the reference level for all 5 dimensions. For let's look at a particular EQ5D3L health state, say the state 22331. So moderate problems with mobility, moderate problems with self-care, extreme problems with usual activities, extreme pain and discomfort, but no anxiety or depression. So if we dummy code that, 1 is going to be dummy code, it'll be the reference level, so it's dummy coded 0, 0. 2 gets the first row of the identity matrix of order 2, so it's coded as 1, 0. And 3 gets the second row of the identity matrix of order 2, so it's dummy coded 0, 1. There will be 10 entries in beta because there are 10 non-reference levels of the 15 levels. So beta 1, for instance, corresponds to moderate problems with mobility, beta 2 to extreme problems with mobility, beta 3 to moderate problems with self-care, and so on. And so if I look at X transpose beta, I get beta 1 plus beta 3 plus beta 6 plus beta 8. So we've got the idea of dummy coding, and we now want to think about how we go about comparing designs. And one common way of doing that is to calculate the information matrix and then to calculate some some function of the information matrix. Let's start by calculating information matrix. And just for ease, I'm going to talk about choice sets of size 2. So my options are A and B, and the probability that A is preferred to B is e to the VA over e to the VA plus e to the VB. So the information matrix is the sum of the information matrices for each of the n choice sets. And here's the summation. So here's a particular choice set C. XC has the dummy coded, as its rows, the dummy coded options in the choice set. And this matrix here represents, or PC beta, is the column vector of probabilities associated with choice set C, given a column of parameters beta. So let's have a look at that in a particular setting. When we look at two health states from the EQ5D3L, suppose the choice set has health states 1, 2, 1, 2, 2, and 2, 1, 2, 1, 2. Those are the options. So we calculate XC by coding 1, 2, 1, 2, 2 and getting 0, 0, 1, 0, 0, 0, 1, 0, 1, 0. That's the first row of the matrix X. We code this option to get this second row of the matrix X. If we suppose that beta has these values, and then we end up with XC times beta transpose, so our entries in V being minus 0.5 and minus 0.7. So the probabilities of the two items being chosen are 0.55 and 0.45. And this gives us this 2 by 2 matrix with 0.248 as down the diagonal and minus 0.248 in the off diagonal. Had the entries in beta been 0, then the entries in that matrix would all have been 0.25 with the same sign. So 0.25 down the diagonal and minus 0.25 on the back diagonal. So let's calculate then this information matrix for the particular choice set. So we're calculating X transpose times this 2 by 2 matrix times X. Here's the 2 by 2 matrix. I've left X transpose because of space. And here's X. So when I calculate the component of the information matrix from that choice set, I get this 10 by 10 matrix. And you'll notice that the final two columns and the final two rows are all 0, because we're not getting any information about the anxiety and depression attribute, because that attribute was set at the same level for the two options in this choice set. That gives us an idea of how to calculate the information matrix. And now we want to think about doing that for a design. So let's take it something much smaller. I just want to play with having two binary attributes in choice sets of size 2. I'll use A and B to represent the attributes. I'll represent the levels of each attribute by 0 and 1. That means we can list the 4 possible options. We get 0, 0, 0, 1, 1, 0, and 1, 1. And if we've got choice sets of size 2, we can then list all of the possible choice sets. So we'll list all the possible choice sets of size 2. So we can have 0, 0 with any of the other 3, and so forth. So we get those choice sets. And now we can calculate the contribution that each of those choice sets would make to the information matrix. So I'm doing that in exactly the same way as I illustrated before. So if I have 0, 0 compared with 0, 1, I'm just getting information about attribute B, but not about attribute A, because both of the options in the choice set have that at the same level, 0. Similarly, when I look at 0, 0 with 1, 0, I'm getting no information about attribute B, although I am getting information about attribute A. And so I can proceed in this way with all 6 choice sets to see what the contribution each of those choice sets would make to the information matrix if they were included in a design. I can then think about listing all of the 63 possible designs for 2 binary options and choice sets of size 2. So a particular row here tells me if their 1 is in this position, it says that choice set is included in the design, and a 0 means that that choice set is not included in the design. So I've ignored design. Design 0, just for computational purposes, is all zeros. So design 1 just contains a single choice set 1, 0, 1, 1. Design 2 has 0, 1, 1, 1. And design 3 has both of those choice sets. And so we go on. Now I can calculate the information matrix, as I say, by adding the appropriate components from the previous slide. So I've just decided to focus on 3 of those 63 designs for a minute. Design 12, D12, has got 0, 0 with 1, 1 and 0, 1 with 1, 0. It's sometimes referred to as the design having the 2 fold-over pairs. So the information matrix for design 12 we get by adding the 2 information matrices for these 2 pairs, and that's what it looks like based on the previous one. Design 33 compares 0, 0 with 0, 1 and 1, 0 with 1, 1. So you can see that it's giving us no information about attribute A. And then looking at design 10, it contains 0, 0 and 1, 1 and 0, 1 with 1, 1. So it's got this information matrix. We need some sort of one number summary of these matrices to be able to compare the designs. And one such summary is the determinant, and it gives it rise to d-optimal designs. And it's probably the most common, I think it is the most common optimality criterion that's used when comparing these designs. And one reason for doing that is the rank order of the designs is the same for d-optimality, regardless of how the attributes are coded. So it's a coding invariant feature, and that's not true for some of the other functions of the matrix that you might, like the trace, that you might choose to use. So in this case, the determinant of M33 is 0, and so it's easy to see. So that suggests we're getting no information, and you can see that we're getting no information about attribute A. Let's now think about how we might compare. So what I've got here are plots of the determinant of the information matrix of various different designs, of the information matrix, various different designs for betas between -2 and 2. So in this first plot, I've got design 2, which is plotted in blue, is always better than design 1, which is plotted in this gold color. In this second plot, design 2 is again the fold-over pairs. Design 1 contains these 2 pairs. And you can see that for values, for this section of this beta 1, beta 2 space, and corresponding section back here, design 1 is actually better than design 2, although for most of the space, design 2 has got better properties, has a larger determinant than does design 1. So that becomes part of the consideration when we think about what do we know about prior values, and how does that have a bearing on what we choose to do with our designs. So there are various construction strategies that are described: random allocation, generator developed designs, which is what I'll be talking about. And then there are computer generated designs based on various different sorts of search algorithms. And unfortunately, I won't have a chance to discuss those tonight. So I want to talk a little bit about the random allocation and then about generator developed designs. So random allocation could be random allocation just from all possible options in the space, but many of the random allocation strategies are based around using the options that form what's called an orthogonal array. And orthogonal arrays are also where we start doing our constructing generator developed designs. So I want to start by defining orthogonal arrays. So an orthogonal array is an R by K array, and column Q has LQ levels. So the columns correspond precisely with the attributes that we were talking about in our choice task before. and the rows correspond to the combinations of levels. So those correspond to the options. And in this array, any two distinct columns, I and j, have each of the Li times Lj distinct ordered pairs equally often. So whilst you could go around hunting for these things, there are two websites. One is a SAS website maintained by Warren Kuffeld. Another one is maintained by Peter Endenbach. And on those sites, you can find large numbers of orthogonal arrays if you want to have a look at them. So I'm going to have a look at an orthogonal array with 16 rows. So that's what this 16 is telling me. And with 6 columns, columns 1, 2, and 6 have each got 4 levels in them. And columns 3, 4, and 5 each have 2 levels in them. So you can see you've just got levels 0, 1, 2, and 3 in these first 2 columns and in the final column. And we're just seeing zeros and ones in columns 3, 4, and 5. So if I look at the first 2 columns, we can look at the ordered pairs. So if I look at a red 0, it has each of 0, 1, 2, and 3 in blue, the 4 red 1s, and so on. So you can see each of the red, blue possible ordered pairs, all 16 of them, appear exactly once each, which is what we need for an orthogonal array. If we look instead at column 1 and column 3, we now have a 4-level attribute and a 2-level attribute. So we have 8 possible ordered pairs, and we can see if we cast our, sort of, if you like, run your fingers down those 2 columns, you can see that each of those ordered pairs appears twice each, which is the property that we need for an orthogonal array. So how does the random allocation work in this case? We're given k, the number of attributes. We're given L1 to Lk, the number of levels for each of those attributes. We decide we want to have choice sets of size m, and we decide we want to have n such choice sets. So that means that we want to find an orthogonal array with the number of rows equal to n times m. And then we randomly group these R treatment combinations, level combinations, into n choice sets of size m. Now let's have a look at what can happen when we do that. So imagine that we have 5 attributes. Each of those attributes has got 4 levels in it. We want to have choice sets of size 2, and we want to have 16 such choice sets. So that means we need to have an array with n times m, which is 32 treatment combinations. So 32 rows in our orthogonal array. So if we go to the SAS site, we can easily find such an array. And what we've done is to take that and construct 100 different designs for m equals 2 by randomly pairing options from this orthogonal array. On 12 occasions, that design had a determinant of m was equal to 0, and so we wouldn't have been able to estimate all of the effects. For the rest of the designs, we calculated what the best possible design is with beta was equal to 0, and the efficiency of the designs ranged from 32% to just under 60%. The average efficiency of these 88 designs was about 45%, and none of the designs where any pair of main effects is uncorrelated. And one of the things I want to emphasize is that this shows that the property of the designs depends not only on the treatment, on the level combinations that are used, but also on how those level combinations are allocated into choice sets. So now let's talk about generated developed designs. So for the estimation of main effects, we need to find, we have given the number of attributes, k, and the number of levels for each of those attributes. We need to find an orthogonal array. Each row or treatment combination in that orthogonal array gives rise to one choice set. And I'm going to obtain the rest of the items in each choice set by adding generators. The addition is carried out component-wise mod LQ in position Q, and we need m-1 generators for choice sets of size m. So the relative performance of the DCEs depends on the combination of generators and the OA. So we've got to link both of those in getting things to work properly for us. So let's have a look at an example of doing this addition component-wise mod LQ. So we want the, thinking about how we constructed the designs for the light bulb study I was showing you before. So we wanted to have 16 choice sets. We had 6 attributes. 1, 2, and 6 had 4 levels. The others were binary. So this option 1, this is the orthogonal array that we start with. Now our first generator has 1 in each position, and so that means we add 1 to each of the entries here. In column 1, that addition is done mod 4. So 0 plus 1 gives us 1, 1 plus 1 gives us 2, 2 plus 1 gives us 3, and 3 plus 1 gives us 0. So sometimes modular arithmetic is referred to as clock arithmetic. So you imagine 0 to 1 to 2 to 3 to 0. The same change is made in column 2 and in column 6. In columns 3, 4, and 5 were binary. So if I've got summarized it here, 0 plus 1 is 1 and 1 plus 1 is 0. So think about binary arithmetic as like a light switch. 1 takes it from off to on, and adding a 1 again takes it from on to off. And so doing that addition gives us the second option in each choice set. To get the third option in each choice set, we add 2 to the 3 attributes with 4 levels. So that's the first, the second, and the sixth. And we leave the binary attributes unchanged. And so this gives us our third option. So we can give some general advice about how to choose the generator entries for attribute Q. I've just looked at levels having between 2 and 8 levels, and choice set sizes between 2 or 3 or 4. So for choice sets of size 2, you may as well just put 1 in every position. If you've got choice sets of size 3, then the first generator stays the same and you have 1 in every position. But in the third, as we saw, we have a 0 for binary attributes. But for attributes with 4 levels, for instance, we have a 2, as we do for 3 and for 5. Whereas for 6, 7, and 8, it's best to have 3 there. And then we've got some comments about what to include if you have 4 choice sets of size 4. So what's the most information that's possible when beta equals 0? And so I've got an expression here that tells you what the maximum determinant that you can get for the information matrix. Just a little caution, this uses orthogonal polynomial coding. And the point of the slide is not what the entries on it are, but that it exists. And so you can make use of it if you want to do so. Just be aware that the information matrix here is actually the original information matrix I defined divided by the number of choice sets, and take heed of the fact that this determinant is a product, 1 for each of the attributes. And when I've got orthogonal polynomial coding, if I look at, say, let's just start by looking at 3 levels. So this first column are the coefficients of a linear polynomial. The second column, the coefficients of a quadratic polynomial. And I'm making a mapping, just as I did with dummy coding and effects coding, where a 0 is replaced by 2 entries. In this case, the first coefficient for the orthogonal polynomial, so -1 over root 2 and 1 over root 6. A 1, again by 2, a 0 and a -2 over root 6, and a 2 by 1 over root 2 and a 1 over root 6. And I've also given examples for binary and quaternary attributes, but you can calculate them for any number. And the main point for showing you this was just to say this is what you use to calculate this information matrix. So do we need to avoid dominated options? If we're going to think about options being dominated, we need to be sure that everybody's going to order the levels of each attribute in the same way, and that certainly seems a reasonable assumption with the EQ5D. As I've said before, a few choice sets with dominated options provides a chance to check that respondents are making rational choices, if you like. But there's some evidence that some respondents may choose an option that is good enough, particularly in larger choice sets, without necessarily looking at all the possibilities. Most of the orthogonal arrays start with everything at the lowest level. So I'll talk about both how to change the initial orthogonal array and observe that if you want to avoid dominated options, it often helps to have a mix of levels in the generator. Some with entries that are close to LQ-1, some with entries that are close to 1, and some in the middle. So reminding you of just the EQ5D3L, the mobility, self-care, usual activities, pain, discomfort, anxiety, and depression. And because the tables tend to start with level 0, I'm now going to have no problems as being level 0, moderate as level 1, and extreme or unable to as level 2. And let's think about getting an initial orthogonal array. I've gotten this one from the SAS website. Now I wanted to have 5 3-level attributes, and I'm going to do that by finding the smallest array that has at least 5 3-level attributes. And that turns out to be the array with 18 runs in it, or 18 rows. And you can see that it has 6 3-level attributes and 1 6-level attribute. And so I can choose any 5 of the first 6 columns to be the orthogonal array that I use for the EQ5D. And so it's all right to remove columns from an orthogonal array because the properties of the orthogonal array are properties that are column dependent, but as soon as you start removing rows, then you're destroying the properties of the array. So here is the 18-run OA, thinking about it for the EQ5D, used the first 5 columns. So this is perfect health, no problems in any dimension, and this is having extreme problems or being unable to. So that's the worst possible state, and this is the best possible state. So we can make changes to this and retain the property of being an orthogonal array by, say, adding 1 mod 3 to columns 3 and 5, and we could stop there. We could decide to add 2 mod 3 to column 4, for instance. And either of these last 2 arrays mean that you don't have anything in your first option which can be dominated by anything else or is dominated by everything else that when you come to use your generators. Why might we use more than one set of generators? We might do it to get a more efficient design. For instance, if we had 7 4-level attributes that we were interested in, we could have one generator with all entries equal to 1, so that would be about 94.5% efficient. If we had one generator with all entries equal to 2, that's 0% efficient. And that's because 2 is a divisor of 4. And so if you have a generator with an entry of 2 mod 4, you're pairing 0 with 2 and 1 with 3 always. And so you've never got a way of comparing 0 and 1 or 0 with 3. But if you use the 2 generators, all 1s and all 2s, then you become 100% efficient. The other reason that you might use more than one set of generators is to allow for some overlap to make the designs easier for respondents. So for instance, in the EQ5D, choice tasks are often given by having only 3 of the 5 health state dimensions vary and having overlap on the other 2. So if I used these 2 generators, I'd have overlap in choice sets that arise from this generator, on pain and discomfort and anxiety and depression, and here on mobility and on self-care. So that can make things easier for respondents to do, because there are less things to have to think about. There's obviously a limit on the number of tasks that an individual can perform, and so that's a reason for having different versions. So if the initial orthogonal array is large, or if you've used several generators, and even more if you've done both, you can end up with a lot of choice sets. And so it's a good idea to subdivide them into versions with fewer sets. There are two ways of doing that. One is, if you've got a spare attribute, to use that to determine the versions. So if you remember, we had a 3 to the 6th by 6 to the 1 in 18. So we could have used the 3-level attribute that we didn't use in constructing the choice sets to define versions, each with 6 choice sets in it. And the advantage of doing that would be that we would know, because that was also an attribute from the orthogonal array, that it featured 2 copies of each level of each of the other attributes. Or we can, if we don't have a spare attribute, or the levels are wrong, we want more choice sets than that arises, we can allocate randomly. Both have been used and seem to work well in practice. What about if we want to include interactions? So we use interactions when we think that the response to one factor depends on the level of another factor. Cost would be a familiar example, but other things might be things like accuracy and waiting time for test results, or the brand of a medicine, whether it's a branded product or a generic, and the pharmacist's recommendation. There might be another instance of where interactions take place. So obviously the model needs to be extended. You've got to have more elements in beta to allow for these interactions that you want to be able to estimate. And we also need to extend the coding. So we don't just have the coding for main effects. We need to have additional terms in the coding to allow for the interaction. And the initial orthogonal array we use needs to have different properties. Instead of looking at pairs of columns, we have to look at what level combinations appear across each subset of 4 columns. That can be reduced if only some interactions are of interest, and then only some sets of 4 columns need to be considered. And the generators that we use need to have a different structure. Each attribute has to have at least one generator with a non-zero entry. That allows us to estimate the main effects for that attribute. And for each pair of attributes where we want to have an interaction between them, we have to have at least one generator with a 0 entry for one of those attributes. And I won't talk about that more now, but just gives you an idea of some of the thinking that's involved. What I want to close with are 3 empirical design comparisons that compare generator-developed designs with D-efficient designs in one way or another. So D-efficient designs are algorithmically constructed by various algorithms and using various bits of software. But the feature that distinguishes them from generator-developed designs is that they use priors. So the generator-developed designs are based on the assumption that beta is equal to 0 in their construction, and they're optimized for that. And a D-efficient design makes other assumptions about the priors, possibly from a pilot study. So in this particular comparison, each design had 24 choice sets, and it used a split sample, so all respondents saw 6 choice sets from each design. And the D-efficient design did not produce significantly lower standard errors, and the overall goodness of fit was not found to be superior in the model from the D-efficient design compared to that from the generator-developed design. And that's contrary to some claims that have been made. And there was another comparison carried out by this group of people, published in 2018, and their interest is in the robustness of efficient designs to misspecification of the assumed prior. And they looked at 10 design strategies, none of which were generator developed. and concluded, or they made a number of conclusions, but the two I want to draw attention to here is the first, it's risky to use an efficient design with uncertain priors. And the paper serves as a reference to support the use of non-efficient, i.e. constructed without a prior design methods in state of choice experiments, of which a generator developed design would be a systematic way of doing that. And using non-zero priors, there are two studies, one that came out in 2015, which is the light bulb study I've been talking about. In the first study, we got information to provide priors to be used in the second study, and we found that prior parameter estimates resulted in a reduction in design performance for main effects and two-factor interactions for the M&L model. And in a study by Mulhern and others, they compared designs to value health states with the EQ5D5L and found that designs with non-zero priors produced more inconsistent coefficients than a design with zero priors. And that's all I have to say. So thank you very much for your attention.
Thanks so much, Debbie. Thanks for that tour de force of all the designs. And it's great to be able to lift the hood of the, and look at some of the maths behind some of these designs. A few questions have come through. I'll just, I've grouped them in a few questions. The first one is regards to, amongst our audience, there are some people who are quite new to DCEs to very experienced practitioners. And there's a question around what kind of textbooks would you suggest for beginners of DCEs?
Okay. So Leonie Burgess and I wrote a book on constructing discrete choice experiments called, I'll just get in to make sure I get it right, it came out with Wiley, Construction of Optimal Stated Choice Experiments. So it provides, you know, all the maths behind the generator developed designs. We published a paper in about 2005, which is designed for practitioners, focused on that. And then there's a book by Hensher, Rose and Green in some order that discusses these sorts of things as well.
Okay, great, thank you. The second group of questions is around D-efficient designs versus the generator developed design.
Yeah.
A lot of people are using D-efficient designs, I guess, and
that's why I had those final slides at the end, where if you've got good priors, then they can do well. They can do better than a generator developed design. And I think a lot of the question is around the robustness of those designs to the mistakes in assuming the assumptions made about the priors that are used.
Okay, yep. And I guess also perhaps the popularity of the D-efficient designs might be, I guess, programs like Engine and Stata and so on, where they could...
Engine, Stata, SAS. I mean, SAS has a design program. There are free packages. I mean, there are other packages other than those. There are papers that have just looked at doing continuous designs rather than exact designs.
Yes.
And for models that they've come out recently in SAS, there's some free stuff available in R as well.
Yep. Okay. So if someone wanted to do build their own generator developed design, do you know whether these programs would also do it?
We have Python code that we're happy to share with people that will do it and will that calculates the efficiency of the information matrices along the lines that I outlined in the talk. I can't comment on what any of the other, I don't believe Stata or SAS do them, and I don't know about anything else.
Do you know whether there are other groups that might be planning to make this a bit more available to the, especially the people who are starting out in this? They might find trying to design their own DCE experimental design a bit too difficult?
Yeah, a bit. I'm not aware of anything. At one stage, we had something that was more, had a web page that was easier to use, but unfortunately that's not being maintained at the moment. Yeah.
Okay, all right. There's another question around the importance of orthogonality, where perhaps when someone constructs a design in that way, they might still exclude certain choice sets because of its implausibility or the dominated alternatives. How important is maintaining that orthogonality? Because some people actually say maybe it's not that important.
Yeah, maybe it's not that important. So I don't think, so design comparison studies that we've carried out suggest that whether or not you've got dominated choice sets doesn't seem to impact on what's happening. So I'm not terribly worried about dominated choice sets. You can, unless you've got a large number of implausible options, generally juggle things so that you can avoid them in the way I was indicating, both with the initial orthogonal array and with your choice of generator. And I think if you want to make a lot of exclusions, I think the best piece of advice I can give someone is to do a simulation and see whether they can recover the assumed betas. Yep. So if you're proposing to use a particular set of choice sets, then simulate data from those choice sets and see whether you, with the particular values of beta, and see if you're recovering those. Safe thing to do with any design.
Great. And I also had a question around calculation of your information matrix. You gave examples of kind of paired comparisons, but what happens if there's more than two, or if there's three objects?
You just have as many rows in the X matrix as there are options in the choice set. And that P, the diagonal P matrix, will become the right size because you'll have a probability for every option in the choice set.
Okay, yep.
If that's making sense.
Yeah, I don't know whether I'm doing justice to the person that asked the question. I think they were also worried about censoring as well. So if you had, say, choice A, B, or C, and someone picked A, you know that they like A more than B or C, but you don't know whether they like B more than C, if that makes sense.
Yeah, you don't get that information without asking more questions. And you can do that by a sort of best approach. So choosing A, or looking at, or asking them to choose the worst of something as well.
Yep.
Yeah. But in terms of the information matrix, as I outlined, when you assume your betas, yeah.
Yep. Someone's asked again about the question of D-efficient versus generator-based. I just wondered if you could just summarize again the pros and cons.
Okay, so maybe I'll just, if we go back, I think, to this so this screen is I'm still screen sharing.
Yep.
So one of the claims about D-efficient designs is that they will produce significantly lower standard errors because you've got a prior value that you're using for your beta, and that you will get a goodness of fit which will be superior to that you get from the generator developed designs. There are also claims about the problem of having dominated choice sets. So the theories, because the D-efficient designs are usually can be tested with values in theoretical comparisons with values that are close to the assumed priors. I think it's perhaps more interesting to look at this empirical design comparison, because you're comparing a D-efficient design with priors determined immediately in advance of the study with a generator developed design. You've got a split sample, so there's no reason to think that the respondents are different from for those that responded to the 2 different designs. And you're finding that the D-efficient designs aren't giving you significantly lower standard errors, nor a superior fit, model fit. So in this case, it would appear that there's not been a gain. And if you look at this next one, non-efficient design methods in stated choice, because it's risky to use an efficient design with uncertain priors.
Mm-hmm.
So I guess those are the empirical comparisons that I think are worth looking at as you think about constructing the designs.
Yep, great, thank you. There's a, I guess, more practical question about, not specifically on designs, but any tips on the best ways to receive data from survey companies?
So we usually get ours as a CSV file in wide format with the code, not with the, say, dummy coding or effects coding, just with the levels. So we'd be receiving K tuples with all the options that were presented in the choice set. We get the respondent ID, and we get which option was chosen, and that's just, we just get that as a CSV file.
Yep. Yeah, and then you do your own manipulation of that.
We do our own manipulation. If we're using R, we can, which is what I tend to use for the analysis, just read in the CSV and take it from there.
Great. Questions been asked about your thoughts on full versus factorial design. What do you think about, do you have a preference for using one or the other, and when should you apply one or the other?
So this comes back partly to what people mean by full and fractional factorials. Mm-hmm. So some people choose to do a design by effectively taking wide format and taking a factorial design in which there are mk factors. So the first k represent option 1, the next k represent option 2, and so on. And the disadvantage, so that's sometimes been called the L to the MA approach, if you look at the literature by Louvier and Henscher and so on, back in the early 2000s. And the disadvantage with that approach is that you can end up with choice sets where options are the same. So you've got to choose a fraction, and there's no way of constraining what's happening in subsets of k factors in that. So I favor taking an orthogonal array and then creating and using a fraction that's just for one option, and then creating other fractions to be the other options in the choice sets, which is what the generator developed approach is doing.
Yep, great. And there's this question about how do you balance, I guess, optimality versus comprehension, or the ease of understanding. Yeah,
statistical efficiency versus respondent efficiency is how I tend to think of it. And I think that's a really hard question. So one of the things that Euroqual favors when using EQ5D, for instance, is to have overlap on 2 levels, because if the post question suggests that respondents find it easier to do the task, and that they find it easier to imagine the health states head-to-head in those situations. I don't think there's an easy answer to that question. I think it's something that we need to think about for each study on a case-by-case basis.
Yes. And I know that we're just on the hour now. Just end off with one last question. Someone was asking about your thoughts about dummy coding versus effects coding. Is there a major difference there, or do you have a preference for one or the other?
Yeah, so I tend to use dummy coding, but I think that the advantage of effects coding, and you know this yourself, Jason, is you can actually get standard errors for every attribute level. You don't have this reference level 0 that stays fixed, and it means that in the coding, everything is a contrast, and so you can sort of move between, say, an orthogonal polynomial coding and an effects coding in an easy way, and you won't find that ease when you move into dummy coding. So I think it's very much a question of what you want to do. But if you want to be able to put a standard error on every level, then if you need to have effects coding, not dummy coding.
Okay, great. I have to draw the line in the sand. I think there's still other questions there, but I've invited people to please write to me. I've put my email there, and I can send these on to Debbie, and she can try to answer some of those for you as well. So with that, just want to thank you so much, Debbie, for sharing your pearls of wisdom, and thank you for all attendees who've joined, and I hope that this has been valuable to you.
Thank you very much. Thank you everyone for coming along, and thanks for the questions.